Hi everyone. So let's see one question of a turbofan engine, single spool turbofan engine or single shaft turbofan engine. So this question was slightly on a trickier side. The students are feeling that they have not provided to solve the question, they have not provided the m dot a, and we need m dot a for solving this question. So let's see, this is not the scenario. You need to understand how to break down the m dot a in this question. Okay. And also we need to understand from this unit what unit they have given. We need to understand this properly. Otherwise which equation you need to use, then that selection of the equation will become difficult. So you need to understand the total enthalpy drop per unit mass flow rate. So this is also a trickier. If you understand very well unit wise the enthalpy balance equation or work balance equation, what unit it holds, if you know that, then it is just a piece of cake for you, right? Otherwise this become difficult. This question will become difficult for you if you just learn the formula equation, and if you don't know the units, then this question will be on a trickier side for you. Okay, otherwise it is straightforward if you know the units and basics. Okay, so let's see the question. A single shaft turbofan engine operates with the fuel air ratio of this much, so it is very small. The total enthalpy drop per unit mass flow rate across the compressor and fan is this much. Now the unit part is very important here. I'll also explain the unit part, what this unit is representing, what term in the mathematical equation it is representing. We need to understand this properly. And this is what your gate questions are. They have done this. Okay, they have not simply stated you that the enthalpy drop across the compressor, enthalpy drop across the turbine. They have not done this. These are the simple way to give. Otherwise if they want to make the question tricky, then they will be using this kind of words, and total enthalpy drop per unit mass flow rate across the compressor. So you need to understand this properly. Okay, respectively fan and compressor, the total temperature drop across the turbine is 460 Kelvin. Calculate the bypass ratio of a turbofan engine. Use CPH. Okay, we'll also see what is the CPH, and they have given 4 options. Okay, so this is the question, and this can be 2-mark question in your gate exam. Okay, so let's see the solution part. Now we need to go from very basic. I'll make sure that you will understand each and every statement they have given in the question. Okay, and so that you will be comfortable with the question. You should not have a fear that we don't know this term or we don't know this term, what is this. Okay, so we'll try to understand. So first of all, you need to start from the enthalpy balance equation, because they all the values they have given, they are indicating towards the enthalpy balance equation or work balance equation. Okay, so let's do the enthalpy or work balance across the compressor and turbine. So you can write one equation. So first you have a fan, then you have compressor, and then you have turbine, right? So fan and compressor, so this fan is known as low pressure compressor and this compressor is known as high pressure compressor when you talk about the turbofan engine, right? I hope you are aware of this. And then you can have a low pressure turbine, then low pressure low pressure turbine, high pressure turbine, depending on the configuration. But here it is only they have given the one turbine, so we are assuming this is a, so turbine is rotating both the low pressure compressor and high pressure compressor. Okay, that is not the issue. I'm not interested on this. I'm interested in how to write the enthalpy balance equation for this configuration. That is an interesting part, and that is slightly difficult. Okay, so let's see. So the first thing is your fan. Your fan is the first component of turbofan engine, right? So your fan will be facing the m dot a, which is the mass flow rate of air. Okay, so your fan will face the mass flow rate of air. So this is an important point. If you don't know which component will be facing which mass flow rate, or let's say your high pressure compressor is facing which mass flow rate, if you don't know, then this question will be again on a difficult side for you. If you know this thing, that fan will be facing which mass flow rate, or my compressor, high pressure compressor, will be facing which mass flow rate, then the question is straightforward. You can simply write the enthalpy balance equation, and you can easily solve this question and get the 2 marks in exam. So that is the important thing, that you should understand which component will be facing what mass flow rate. Now fan, we know fan will be facing m dot a, the directly fan is facing the mass rate of air. Now compressor will be facing m dot h, which is core mass flow rate, or a hot mass flow rate. We name it as a hot mass flow rate in our convention, or you sometime in book you will find this a core mass flow rate. Okay, that means inside the core engine how much mass is entering for my combustion. that is known as the m dot h or m dot c. M dot c, that means core mass flow rate. Okay, but in our notation, m dot c represent the cold mass flow rate. I'll not go into detail of that, otherwise this notation will make you confused. So that is okay. So depending on your bypass ratio, your fan will be split some amount, most of the amount of mass flow rate into the cold area, and the few amount of mass flow rate into the for the core engine, that means m dot h, hot mass flow rate. Okay, so your compressor, high pressure compressor, is facing your m dot h, that means hot mass flow rate. Hot mass flow rate. And what is this? This is air mass flow rate. Right now your turbine is facing what? The turbine is facing after the combustion, right? It is m dot f, that means fuel flow rate plus hot mass flow rate, m dot h. So you need to have the mass conservation as well, right? Okay, so these are the things that you need to understand. Now we'll write the enthalpy balance equation, but before that you need to understand your m dot a is nothing but what? M dot a is nothing but cold plus hot. Cold mass flow rate plus hot mass flow rate. Addition of this will give you the total mass flow rate. So this is the total mass flow rate, that means air mass flow rate. Okay, okay, so this equation we need to keep in our mind. This will help you. Now I hope you understood this much. Now we'll proceed ahead with the writing the enthalpy balance equation. So now we can write the enthalpy balance. So okay, we'll write enthalpy balance directly, then I'll explain you this term, the total enthalpy drop across the compressor and fan. Okay, so this can be written as, so this is direct enthalpy balance equation. So first we are writing for the fan. Okay, so fan component is facing the air mass rate, so it is associated with the m dot a, and the enthalpy drop will be delta h naught, and this is fan, right? So I'll give suffix as a f. Okay, now the high pressure compressor, which is your this one, is facing what? This one is facing hot mass flow rate, so it will be subjected to m dot h and delta h naught c. We'll write this as c. Okay, then your turbine comes, right? So this will be m dot f, fuel mass flow rate plus hot mass flow rate. Sometime this hot mass flow rate you will find in your book this as a m dot c. This is one and the same thing. This is core mass flow rate. Okay, core and cold mass flow rate both are the different thing, both are different. Okay, please don't get confused in this. Now they have given what they have given, the total temperature drop across the turbine and cp value for a hot. So this cph is representing the hot gases specific heat. Okay, so this can be written as cp, okay, cph for gases and delta T naught across turbine. Now I'll explain you about the unit. Okay, and this term is representing this one, so it will be comfortable for everyone. And this one is, and turbine is subjected to this expression. Okay, now we need to understand unit wise. Okay, now if you see, now you should understand the total enthalpy drop per unit mass flow rate, what it is, that you need to understand. So when you write delta h naught, okay, when you write delta h naught is what? This is nothing but cp and delta t naught, right? When you break the term h, this is cpt, right? When you write h naught, this is cpt naught, right? When you write capital H, naught, then this becomes mass flow rate, then cp, then t naught. Okay, so now you need to understand unit wise. They are saying unit wise, if you see unit wise, when you see this cp, you can write this as a kilojoule per kg Kelvin or joules per kg Kelvin, right? But here they have given in terms of kilojoules, so I'll write this as a kilojoule per kg Kelvin, kilojoule per kg Kelvin. And what is the unit of temperature? Temperature is nothing but Kelvin. So when you simplify this Kelvin will get cancelled out, right? And you'll end up getting this as a simply kilojoule per kg. Okay, and this is what this much. This is what they have given in your question. They have given the total enthalpy drop per unit mass flow rate. So what is the total enthalpy drop? Total enthalpy is this much, that is captured in total temperature. Okay, and when you multiply with cp, that becomes the total enthalpy. Okay, I hope this is clear. And the unit wise, if you see kilojoule per kg, here they have also given in kilojoule per kg. So what they have given in the question, they have given in the question this term. Okay, this term they have provided. Similarly here they also provide this term. Okay, now comes to the turbine, what they have provided, you need to understand that as well. Okay, so turbine, if you see, they have provided the total temperature drop across the turbine is 460 Kelvin. So they have provided only this term, this one. They have not provided with the CP. Okay, you need to multiply CP separately to, because they have already provided the CP, right? So now my equation will become this much. Okay, so CP multiply by temperature, now it will become my enthalpy. Now this is completely enthalpy balance equation when you multiply mass flow rate as well. Okay, I hope you understood this equation and as well as what this each and every term is representing and taking the units. Okay, fine. So let's proceed ahead with the, now the issue starts here is they have provided this term m dot f. We are having, anyhow we are having the fuel flow rate, fuel to air ratio we are having, so m dot f we can have. Now the challenging part is that we have m dot f, anyhow fuel flow rate is already provided, fuel to air ratio is already provided, so m dot f we are having. M dot h is also the calculating part, because we need to have a bypass ratio, right, beta. So beta is what, beta is nothing but m dot c divided by m dot h. If you see this equation carefully, in the equation we are nowhere we are having the m dot c, we are not having m dot c, right? We are also not having the m dot a as well. Okay, m dot a is not provided, air flow rate is not provided, so that is the issue. Now you need to break down this equation. You might think that this is a straightforward equation, we'll substitute all the values and we'll get the answer, but the thing is they have not provided the m dot a as well, they have not provided the m dot c as well, so you need to modify this equation in terms of the beta. And your question will, the question is asking for your beta only, right? So you need to modify this equation. Now you please see this carefully, how I'm modifying this equation to arrive at the beta solution, which is your bypass ratio. So now the thing is, I told you this m dot a can be written as m dot c plus m dot h. Cold mass flow rate plus hot mass flow rate will give you the total mass flow rate. Addition of this is the mass conservation. Okay, m dot c cold and hot, summation of these two will be total mass flow rate, which is air mass flow rate. Okay, so air is entering inside the engine, but they are in the turbofan engine they get separate due to the bypass ratio in terms of m dot c and m dot h. Most of the air will be going to the cold mass flow rate section, and few amount of air will be entering inside the core engine. I hope you have studied the turbofan engine properly. Now I can write m dot a as m dot c plus m dot h, right? And we'll keep it delta t naught, delta h naught f, plus this can be written as m dot h delta h naught for a high pressure compressor. Now I'll take common from this term m dot h. Why I'm taking this? Because when I take m dot h common, I'll get m dot f divided by m dot h, and this is what they have given in the question, that fuel to air flow rate, air ratio, right? So I'll take m dot h common, and this will become m dot f divided by m dot h plus 1 cph delta t naught t turbine. Okay, so let me give you this as well. So your f fuel to air ratio is given as, fuel to air ratio is nothing but m dot f divided by m dot h. Also you need to understand that m dot f is the smaller quantity. Okay, it is very small. Fuel flow rate is very small compared to the hot mass flow rate or compared to the total flow rate. So m dot h is very small value, m dot h is a very big value. That is the reason you are getting a ratio, as a this, which is very small. Sometimes, usually we try to neglect this value compared to the other values, but here they have provided, so we need to consider this, and this value is 0.0234. Okay, we need to use this. So this term is known to you. Okay, take both the side, divide both the side m dot h. Okay, now we'll divide m dot h on both the sides. So this will be what, this will be m dot h, and this will become 1, this will become 1, right? And again this will be 1, and this will be also 1, right? So now my equation get modified. Now this is representing what, this is representing beta, which is your bypass ratio, m dot c divided by m dot h. Now you understand, I hope you understand that how I have modified this equation to arrive to have a term beta in my equation to solve the question. Okay, I hope this is clear to you. Now I'll simplify this, so I'll write this as beta plus 1 delta h naught f. Okay, and this is just, so this is just unity. Delta h naught c is equals to unity, then this is fuel to air ratio plus 1 c, okay, cph delta t naught turbine. Okay, so this is my final equation. Now I'll substitute all the values in this equation and simplify for beta. So beta can be simplified by f plus 1 cph delta t naught t divided by, okay, also you need to take this term into right hand side, so it will be in a subtraction of delta h naught c, and this term will be in a denominator, delta h naught for a fan. Okay, this is for fan. So in exam you need to do this simplification very quickly. For that you need to have a practice of such questions, right? So now what you need to do, you need to substitute all the values in this. F is already provided, okay, which is 0.0234 plus 1. CPH is already provided, which is 1.156. Now be careful, they have given in terms of kilojoule per kg. Okay, so you need to be careful about this for this. Okay, so 1.156, we need to multiply 10 to the power 3. So let's keep this whole equation in SI unit. Okay, so that will not have any issue regarding the unit. And what is the delta T naught in Kelvin? This is 460 Kelvin. Okay, temperature drop across the turbine 460. Okay, you see the expansion, how much expansion has been done. Now delta H naught for high pressure compressor, this one, or this term, this is given as okay, 331.84. okay, again you have to multiply 10 to the power 3 in this, because they have given in kilojoule per kg, so we'll keep all the term in joules per kg, so that will not have a unit issue. But anyway, at the end we'll take 10 to the power 3, 10 to the power 3 common from the numerator, and in the denominator we'll also have a 10 to the power 3. It will get cancelled out. You can simplify, but this is what you have to do in the exam. You need not to take this 10 to the power 3, okay, and this will comes from practice. You directly substitute, at the end 10 to the power 3 will get cancelled out, you'll end up getting the actual answer. Okay, this in the denominator you have a fan component, so enthalpy drop for a fan is 70.34 into 10 to the power 3. Now this 10 to the power 3, this 10 to the power 3 take common, and you can cancel out from the numerator and denominator, and at the end you will end up getting this as a, okay, sorry, you have a 1 plus beta here, 1 plus beta here. And if you solve the right hand side this term, you'll end up getting this as a 3.01. Now solve for beta, this will be 2.01. Approximately you can write this as a 2. Okay, so your bypass ratio comes out to be 2, right? What is this bypass ratio? M dot C divided by M dot H. If you see this M dot C, you can write this as twice of M dot H. Now what do you understand by this? Anyway, you got the answer, right? But you should have the understanding, and this is what the interview questions are. So if you see this engine, it is having your hot mass, sorry, your cold mass flow rate. Okay, cold mass flow rate is a twice of the hot mass flow rate. This is what? This is hot mass flow rate, M dot H, right? So let's say your hot mass flow rate is 20 kg per second. So here what will be the core mass flow rate? M dot C can be 40 kg per second. So you see your cold mass flow rate is the twice of the hot mass flow rate. Okay, I told you already that most of the air will be splitting and it will be going into the cold section, and few amount of the air will be entering into the core section or hot section. Okay, so they can also frame this question that at the end they can provide you the M dot H or M dot C, and they can ask you for computing the M dot C or M dot H. Simple. So that this can be also the possibility of framing a question. Okay, so I hope you understood how to solve for bypass ratio or beta. Don't think that they have not provided the M dot A, then how we will solve the question. You need to break down this M dot A in terms of the M dot C and M dot H. then you can easily solve this question. So option B is correct. Okay, I hope you have learned a lot from this question. Okay, how to modify this question unit wise, you how to see the question. Okay, unit wise, that is also important. Okay, I think you can also keep this equation in your notes. This can be a good formula for solving the turbofan questions. Okay, efficiency was not provided, so I have not accounted for efficiency. Efficiency will take this as 100%. Okay, anyway, so I think this is good enough. So let's meet in the next lecture, guys. Bye bye.